Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the join button below for more details. My name is Sava, and today we're investigating the distribution feeding procedures in Python, and following up from the prior video where we investigated some simple distributions such as the normal distribution, the Cauchy distribution, we are advancing to generalized distribution families that can accommodate a very wide range of different asset return distributions. And we start by the generalized error or the generalized normal distribution and investigate its application in Python to a wide range of asset classes and see just how well those flexible distribution families, if you allow some parameters to be optimized using maximum likelihood, how well do they actually capture the real-world dynamics of asset returns. First, let's discuss the packages that we'll need. We obviously need NumPy for arrays and pandas for data frames. We'll also need some scipy packages for our distribution function calculations as well as for the maximum likelihood estimation. So we'll need the scipy special package, and I'll just import it as SPSP. And we'll also need the scipy optimise package for maximum likelihood. Mind the American spelling of the word optimize here. We'll need Yahoo Finance or Y Finance package to retrieve real-world prices. And we'll also need, for some visualizations, the usual suspect matplotlib pyplot. So having imported those packages, we can consider the distribution itself and the sample we'll seek to apply it to. For that, we'll need the probability density function and the cumulative distribution function of the error distribution. So let's specify our sample first. So first we need to specify the ticker, and let's start with S&P 500 as usual, and then investigate its applicability to other asset markets. So the Yahoo Finance ticker for the S&P 500 is GSPC. Then let's select the start date and the end date, and let's go for 5 years worth of most recent data. So let's start at November end 2017 and end at November end 2022, and we can retrieve this data using Yahoo Finance download. So the prices is a Yahoo Finance download command. We specify the ticker, the start date, the end date, and we need the closing prices here just for simplicity. And here we'll retrieve our prices, and if we run the script now, we'll see that the prices will be a pandas series starting from again November end 2017 and ending at November end 2022, just as we wanted. What it means is that we now can convert those into returns, as that's the goodness of fit of returns we seek to investigate, as well as sorting them to calculate the empirical distribution function and to evaluate all other steps way simpler and way more intuitively. So the returns can be calculated using just simple holding period formula. Here we need to mind that the prices series is indexed, so we would like to either reset indices or just convert them to NumPy arrays as usual. I'll opt for the latter trick, so I'll select the prices from the second day onwards and divide them by the prices from the first day until the penultimate day, so second to last day, and subtract 1, allowing us to calculate returns. If we check that, we'll see that we have correctly calculated the returns from start to end, and that's our NumPy array. Again, if you would like them in percentages, you can just multiply them by 100, but I prefer to work with them as they are, as it simplifies some of the other applications. So again, feel free to either multiply by 100 or not. And now, for the empirical distribution function application, we'll need to sort those returns. We can just use the NumPy sort function here and apply it to the returns array. By default, it will sort them from lowest to highest, and that's exactly what we need. So we can see that the lowest return ever over those 5 years was minus 12% in a day, and the highest was plus 9% in a day, which is again reasonable for S&P 500. And now we can calculate the empirical distribution function, which would basically map those returns from lowest to highest to their occurrences. So empirical distribution function, EDF, is just an NumPy range from 1 until the length of returns plus 1. Again, as NumPy range is exclusive, non-inclusive that is, and we divide it by the length of returns. Now we can actually have a look at how it looks. Now we can actually have a look at the empirical distribution function visualization. So if we plot the returns alongside the empirical distribution function, so returns on the x-axis and the probabilities on the y-axis, that's how conventionally you visualize those. We'll see the curve, the actual historical distribution of returns that we'll seek to model using some mathematical function. In our case, that's the generalized error or generalized normal function. And for that, we'll need to know what sort of parameters do we need to plug into this function to represent our data the best. The concept behind the generalized error or generalized normal distribution is to start at the normal distribution and try to preserve the same mathematics, but allow for various thickness of tails. And the easiest analogy to the normal distribution can be spotted here, in this particular spot of the cumulative distribution function formula, where you raise scaled x, so scaled returns in our case, minus the location parameter divided by the scale parameter, so that kind of is a z-stat, if you think in normal distribution terms, raised to the power of the shape parameter. Well, for the normal distribution, you'll square your z-stat and plug it into the exponential function to evaluate the distribution function at a particular place along the line. However, if you allow this to be not only squared, but raised to any sort of non-negative power, then you can model a wide range of tails, from very thick tails to tails that are even thinner than the normal distribution function tails. And that goes as follows. If you raise your z-stat to a very high power, then your tails will dissipate very quickly. The higher this power is, the faster the tails dissipate. The lower it is, the thicker the tails remain for more substantial departures from the mean, for more substantial z-stats in terms of the magnitude. So again, the distribution will remain symmetric. The logic of scaling your x, scaling your returns, by subtracting the location parameter and dividing by the scale parameter, so basically z-scoring your data remains. What changes is simply the speed at which the distribution tails converge to 0 the further away you go from the mean. Again, for the distribution shape parameter equal to 2, you'll have the normal distribution, the conventional Gaussian tails, as we square scaled x in this application. If you select the shape parameter to be equal to 1, you'll get the Laplace distribution. We've got a separate video on the Laplace distribution here if you're interested in this particular application. So the generalized error distribution already accommodates both of those very common distribution in itself. This is how flexible it is. And we can already see that given that Laplace distribution has quite a bit thicker tails than the normal distribution has. If you remember, the Laplace distribution has an axis-caddices of 3, and the normal distribution has an axis-caddices of 0, you will see how a reduction in the shape parameter allows you to generate fatter tails. But you needn't stop at 1. You can go lower than 1 and generate tails that are even thicker than Laplace. What is also quite an interesting and sometimes a welcome feature of the generalized error distribution for some of the finance applications in particular is that no matter how low you select your shape parameter to be, all of your distributions will be finite variance. So you will never generate a pathological distribution that would be, for example, unapplicable to do a gauge model with or to value options with. The variance will always exist. It's just that sometimes your tails can be quite fat. And the lower the shape parameter is, the fatter the tails are. So we can look at the shape parameter and make a qualitative judgment about how thick the tails of this asset returns are. So keeping that in mind, we can calculate the conventional mean and standard deviation of our distribution and use those as the starting parameters of our location and scale, and start with 2 as our shape parameter to allow the algorithm to converge from the normality assumption to something that represents our data much better. So the mean would be just the NumPy average of our returns. The standard deviation would be just the standard deviation of returns. Again, the NumPy functions do the job here. And now we can proceed to our maximum likelihood estimations using the mean, standard deviation, and the shape parameter of 2 that's typical for the normal distribution as our input values for the maximum likelihood. To perform maximum likelihood, we need to define a function, and let's call it generalized error distribution optimization. And we need to specify the argument of this function, and I'll call it k. K will be the vector of our distribution parameters. So k0 would be the location parameter, k1 will be the scale parameter, and k2 would be the shape parameter. Here, we can allow the location parameter to be anything we like. It can be negative, it can be positive, it can be 0. However, the scale and shape parameters can only be positive. So we could potentially input this restriction into the optimizer itself. However, it is often way easier to just implement that in the function when you define it. And to do that, I'll simply take the absolute values of k1 and k2 within the function so that we never encounter errors due to the optimizer picking negative values or 0 values for our shape and scale parameters. Having avoided this particular issue, we can actually calculate our probability density function using the mathematical formula at the top. We need the shape parameter first, which is k2. Then we'll need to divide it by 2 times the scale parameter, so k1, times the gamma function. Gamma function, again, is a generalization of the factorial to all real and even complex, to be honest, numbers. And that's why we need the scipy special package 4, because it is only available in the scipy special package. It's considered quite an advanced mathematical function. So we do SPSP gamma, which is the gamma function in the scipy special package, and input a 1 over the shape parameter, so 1 over k2, as our argument. Here we can see an interesting relationship between the probability density function of generalized error distribution and the probability density function of the normal distribution, as you have got 2 times scale in the denominator, which does recall sigmas in the denominator when you evaluate the probability density function of normal distribution. What is also quite cool is that if you plug in the shape value of 2, you'll have the gamma function of a half, which is actually a square root expression involving pi. And this is where pi comes into the normal distribution probability density function, just from a particular case of a gamma function involving a fractional number. But this out of the way, we can now implement our exponential term, which will be the NumPy exponent, the easiest way to implement that on an array in one go. And then we introduce a negative absolute value of our x, which are returns, minus the location parameter, which is k0, k0, divided by the scale parameter, which is k1, and then we need to raise it to the power of the shape parameter, or k2. And that does the trick, allowing us to calculate the probability density function for every single observations we've got. And now we need to return the log likelihood for ease of optimization. Again, in terms of the concept, you try to maximize the product of all the probability density functions of all of the likelihoods evaluated at every single observation. However, as it's exactly the same concept to evaluate the non-negative variable, and again, all of the probability density functions are non-negative by definition, and their logarithm, we can actually maximize the logarithm of the product of probability density functions, which quite nicely corresponds to a sum of their logs, because logarithms convert products into sums. And maximizing a sum, or minimizing a sum, optimizing a sum in general, is way easier than optimizing a product for just computational reasons. So that's why log likelihood is the way to go. So we return our log likelihood. So we return the sum of logarithms of the probability density functions evaluated at all of our observations. A final caveat we need to accommodate here is that scipy.optimise package allows only to minimize functions and not to maximize them. So we want maximum likelihood, so we just put a minus in front, and well, we minimize something negative, which is equivalent to maximizing something positive. It's as easy as that. Now we can actually apply this optimization, and the result of the optimization will be a scipy.optimise minimize function applied to our function which is defined. Then we need to input our starting values, which are the mean, the standard deviation, and the starting shape parameter, which is 2. So we start with the normal distribution and try to converge to the best fit from there. And then we need to apply or specify the optimization method. And again, for relatively easy optimization algorithms that are smooth, and we've got all smooth functions here, Nelder-Mead is the algorithm that works the best. Again, you can play around with them. The next go-to algorithm would be Powell, which performs better when your functions can be non-smooth or when your optimization algorithm is very cumbersome. However, here Nelder-Mead would work just fine. And then we can simply print the result of our optimization and check how well it goes along the way. And we can see that the optimization has been terminated successfully. We have got the function value of, well, if we remember that we put a minus in front, this is our log likelihood, if we just throw away the minus. And we can see the vector of the optimal parameters we have converged to by maximizing our log likelihood. And the most important parameter we need to check is the final one, which is the shape parameter. And we can see that it's equal to 0.86 approximately, which is lower than 2 and even lower than 1, which means that the tails of the S&P 500 returns are thicker than the ones suggested by the normal distribution and thicker than the ones suggested by the Laplace distribution, because the shape parameter is less than 1. And that's a nice qualitative interpretation that just studying the shape parameter can produce. And well, we have got our optimal parameters stored in the result variable. So we actually can refer to the result variable and retrieve our optimal distribution parameters for further calculations. The parameters will be stored under res.x. So res.x are the optimal arguments that we have calculated. So our location parameter GD loc equals the, well, resx0, which is basically the first element of this array. Our GD scale would be the absolute value of the second result. Again, the absolute value here is to take into account this particular manipulation to avoid negative parameters. And the shape is the final element of this array. And given the fact how important the shape parameter is, we can print that and explain what it is. So the shape parameter of the best fitting distribution equals, and then we can well, just convert it into a nicely readable number. So basically round our shape parameter to 4 digits and run the procedure again. And we can see that the shape parameter of the best fitting distribution equals 0.86 on average, which already gives us a nice idea in terms of how thick the tails are or how flat the tails are. Now, having calculated all the parameters, we can actually calculate the cumulative distribution function and evaluate the goodness of fit using something like Kolmogorov-Smirnov test. Again, for pretty much any goodness of fit test, you need the cumulative distribution function, comparing it to the empirical function. So let's calculate the CDF, the cumulative distribution function, using the formula above. So 1/2 plus numpy sine of returns minus the location parameter divided by 2. And then we multiply it by the most advanced function from scipy special that we'll use today, which is the gamma incomplete function that takes 2 arguments. One of them is 1 over the shape parameter, and the other one is the absolute value of returns minus the location parameter divided by the scale parameter raised to the power of the shape parameter. And that concludes our cumulative distribution function calculations. And now we can visualize those alongside the empirical distribution function. So we can plot the empirical distribution function first, then we can plot the cumulative distribution function, and then we can apply PLT show. And we see that the fit is surprisingly good. We have got a slight departure of our smooth orange theoretical distribution function from the empirical distribution function somewhere along the hump. However, this is way better fit, even visually, than some of the more restrictive distributions, like the normal distribution of the Cauchy distribution. So we already see, even qualitatively, even on the graph, how well does the flexibility of those generalized distribution families, such as generalized error, pay off in real-world applications. However, to put a number to this goodness of fit, let's apply Kolmogorov-Smirnov and calculate the supremum, which is the maximum distance between the empirical and the cumulative distribution function of the theoretical function we're using. So it's the maximum of the absolute deviations between EDF and CDF. And then we can calculate the p-value, which will determine the goodness of fit, using the exponent of minus supremum squared times the length of returns, which is our sample size. Then we can print what the p-value actually is. And then we can round our p-value times 100 to 4 decimals and add a percentage sign for simplicity of interpretation. And finally, we can make the test result and evaluate whether the distribution fits or not, whether the null hypothesis of fit is accepted or violated. So if the p-value is less than 0.1, feel free to select any confidence level you are comfortable with. We can print that the distribution does not fit the data, and else we can print that the distribution fits the data. And the only thing remaining is to run the script, and we see that the Kolmogorov-Smirnov test p-value is around 42%, which does not violate the null hypothesis, and that means that the generalized error distribution with the shape parameter of 0.86 fits S&P 500 returns remarkably well. Now let's run it on some other assets. For example, we can check individual stocks like Tesla and see whether Tesla tails would be nicely accommodated by some value of the shape parameter. And yeah, actually, given the fact that this is quite close to 1, the distribution of Tesla returns has been very close to the Laplace distribution. And the p-value is again quite high, meaning that the distribution fits the data very well. We can check some of the more established stocks, let's say Caterpillar, and see what the results are for those. Again, quite intuitively, the shape parameter for Caterpillar is a little bit higher, meaning that the tails are a little bit thinner than the one for the index and the one for Tesla, which is quite a volatile stock. And we can see that the null hypothesis of fit is not violated once again, which is good news. We can test for other stock indices. For example, we can test FTSE and see how well the generalized error distribution fits a stock market index from another country. We can see that the fit is still quite decent. We can also test other markets. Let's say we can test the Euro-USD foreign exchange market. And here we have got, again, very good fit, and the shape parameter is higher, meaning that foreign exchange returns are quite a bit closer to normal than the one of stock markets, which is quite a common stylized fact. We can even check cryptocurrencies like Bitcoin and see what the results are for Bitcoin. For Bitcoin, the fit is again remarkably well achieved, and the shape parameter is lower than 1, again highlighting the fact that Bitcoin tails are quite fat. We can even check for the more speculative cryptocurrencies like Dogecoin, and for that we'll see that The shape parameter is now even lower, meaning that the tails are even fatter, but still the fit, the null hypothesis of fit is not violated. And that's all there is for the implementation of the generalized error distribution and its goodness of fit procedure in Python using Yahoo Finance real-world financial data, maximum likelihood estimations using scipy.optimise, and some nice tricks using scipy special statistical functions. Please leave a like on this video if you found it helpful. In the comments below, I may do see any further suggestions for videos you would like me to record, and please don't forget to subscribe to our channel and consider support us on Patreon. Thank you very much, and stay tuned.